I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to see the topic Maxwell's equation in integral and differential form. This is for the course Electromagnetic Fields. The valuable work done by James Clerk Maxwell is discovering electromagnetic waves. The time-varying fields were discussed by Faraday and Hertz, but the theoretical analysis was done by Maxwell. So the Maxwell's equations are a set of four expressions which are derived from Ampere's law, Faraday's law, and Gauss law for electric field and Gauss law for magnetic field. So these four equations are written in the two forms. One is called integral form and another one is called differential form. So the first equation we are going to see, the Maxwell's equation derived from Ampere's law. So according to Ampere's law, the magnetic field around the closed loop is equal to the total current enclosed. So it will be given by the expression integral over the closed surface h dot dl is equal to I. But we know that current I is equal to current density, integral of current density, that is I is given by integral over the surface j dot ds. So by combining these two equations, we can write according to Ampere's law, integral over the closed surface h dot dl is equal to integral of j ds. Here Maxwell included the displacement current density also, so the expression will be j plus dou d by dou t. So this dou d by dou t is called displacement current, j is called conduction current, and this equation integral of h dot dl is equal to surface integral of j plus dou d by dou t ds is called Maxwell's equation derived from Ampere's law. And this according to Stokes theorem, we can write the line integral into surface integral. So in the equation number 1, we can replace integral of h dot dl by integral over the surface area del cross h dot ds. So this is according to Stokes theorem. So the right hand side of equation 3 is integral of surface area j plus dou d by dou t ds, that is the current density integration. So by removing here in the equation, both sides are the surface integrals, and by removing the integrals we can write del cross h is equal to j plus dou d by dou t. This equation is differential equation of Maxwell's equation derived from Ampere's law. And for the second equation, we are taking the Faraday's law. So according to Faraday's law, the electromagnetic force is given by E is equal to minus d phi by dt. And here this E can also be written as minus of d by dt of integral of b dot ds. So this can be written as integral of E dot dl, because the electromagnetic force can be written as integral of E dot dl is equal to minus in surface integral of dou b by dou t dot ds. And this is called Maxwell's equation, second equation derived from the Gauss law. And next is by removing the integrals, we get del cross E is equal to dou b by dou t. And this is the Maxwell's equation in differential form derived from Faraday's law. And according to Gauss law, we can write the total displacement density, that is flux density, is equal to total charge enclosed, that is surface integral of b dot ds equal to q. But we know that the charge q is nothing but integral of charge density. So we can write the right hand side expression as q as integral of rho dv. So integral of b dot ds equal to integral of rho dv. So this is called Maxwell's third equation derived from Gauss law, and by removing the integral we can get del dot d is equal to rho. So this is the Maxwell's equation in differential form. And next is we are going to see Maxwell Gauss electric field equation, integral of B dot ds equal to 0, and del dot B in differential form it is del dot B is equal to 0. So this is Maxwell's field equation derived from Gauss law. And for time varying fields we can write J is equal to sigma E, del dot J is equal to minus dou rho V by dou T, and the force F is equal to QE, dV is equal to L cross B dl. And the Maxwell's 4 equation in free space in integral form, this can be written as H dot dl is equal to surface integral of dou D by dou T dot ds, and second equation integral of E dot dl is equal to minus dou B by dou T dot ds. Third equation B dot ds equal to 0 and B dot ds equal to 0. The fourth equation. In free space there is no charge density. So in the third equation D dot bs is left as 0 on the right hand side. And the differential form del cross H is equal to dou D by dou T, del cross E is equal to minus dou B by dou T, del dot B is equal to 0, del dot D also equal to 0. And for time varying fields, this each parameter, for example if we take T for harmonically varying field, this flux density vector D can be written as D naught e power j omega t. This D naught is the magnitude and e power j omega t represents the time varying field. So by differentiating this D, flux density dou D by dou T gives j omega D naught e power j omega t. But we know that D naught e power j omega t is flux density D. So this can be substituted. So dou D by dou T is j omega D. By substituting all these values, we can write the Maxwell's equations for harmonically varying fields as integral of H dot dl is j plus j omega sigma plus j omega into integral of E dot ds, and integral of E dot dl is j omega mu into integral of H dot ds, and integral of B dot ds equal to integral over the surface area rho dv, and integral of B dot ds equal to 0. So this is integral form for harmonically varying fields. And Maxwell's equation in differential form for harmonically varying fields as del cross H is equal to sigma plus j omega E, and del cross E is equal to minus j omega mu H, del dot D is equal to rho, del dot B is equal to 0. And here this table gives the Maxwell's 4 equations in different form and derived from the various law. And the previous table is for integral form and this is differential form. Thank you.